I want to talk today about how quickly gas particles move, because I've said in past videos, and what we understand about matter is that gas particles are pretty free to move around. We kind of get that from kinetic molecular theory, that the more free particles are to move around, then the more we can define the phase of matter based on that freedom and flexibility of motion. So how well can they move past each other? How quickly do they move? How much space is between them? All of that factors in to kind of the way that we think about the different phases of matter. And gases are pretty unique because they move around so quickly, there's such large spaces between them, and the particles themselves are fairly teeny tiny. So there's all these kind of interesting things like gas laws, but we can also use them to study what is called molecular speed and the effects of kind of the movement of those gases from the containers that they're in. So we're going to talk about Graham's law of effusion in this video as well. In order to get to Graham's law of effusion, though, we need to talk about RMS molecular speed. RMS stands for root mean square. Root mean square. Molecular speed. And what that really means is that we're taking the average molecular speed given an average kinetic energy, which sounds like we're making a lot of assumptions there, and we kind of are. I mean, we can't have a little stopwatch and a meter stick and a little atomic nanometer stick to look at the rate at which individual molecules are going to be moving. So we have to think about them in terms of an average kinetic energy. And we know that average kinetic energy is something that we can measure with a temperature scale, right? The average kinetic energy we can compare to a scale. That scale will give us an idea of kind of hotness and coldness of a substance. And if we want to think about this in terms of individual molecules, because we're chemists, so we think about things on the particle level, then the average molecular speed given that average kinetic energy is this RMS molecular speed. And this is something that we can actually kind of put some numbers to, and some numbers that give us a general sense of how quickly these things are actually moving. So a couple things. The RMS molecular speed is abbreviated with a U, which I always say is kind of a catch-all variable for when we've run out of variables, then this is the one that's left over. U is also used for things like internal energy, which is probably why it's used here if I was to guess, but I don't know 100% sure on that. So it's U. That's equivalent to the square root of 3RT, T meaning the absolute temperature. So we have to think about things in terms of Kelvin. So let me write this out. Absolute temp. So the absolute temperature, of course, is in our SI unit of Kelvin. MM here is your molar mass. And R is the same gas constant that we've talked about in past videos with our various gas laws like Boyle's law and the ideal gas law. That R is the same, but there's a useful version of R that is 8.31, which is the same as it is in kilopascals, but it's equal to joules per mole Kelvin. 8.31 joules per mole Kelvin, or another way to write that, if we unpack the joules here, is 8.31 kilogram meter squared per second squared, and then mole Kelvin. So recall that a joule is a kilogram meter squared per second squared. So if I kind of plug that in, then that'll actually make these units make sense because we have our Kelvin here. The molar mass here has to be in, because of the joule, it has to be in kilograms per mole. So that's kind of a weirdness because we don't usually have to convert molar mass. We usually just take it from the periodic table, and that's in grams per mole. But we have to, in order to use RMS molecular speeds equation here, we have to use kilograms per mole. And you can see that there's no pressure term in here, so this is independent of pressure. So this is just the average molecular speed based on the movement and the size, essentially, of these things. So we can use that equation to solve problems that look like this. If you have an identity of the gas, let's take diatomic nitrogen, for example, and a temperature, then we can figure out the RMS molecular speed. So our equation is this, 3RT over the molar mass. So our temperature is given in Celsius, 455 degrees C. It's an absolute temperature, so we need to convert to Kelvin. So when we add our 273.15, then we end up with 728 Kelvin. And then for dinitrogen, my diatomic nitrogen, my elemental nitrogen, then the molar mass is 28.02 grams per mole. So one nitrogen, 14.01, I multiplied by 2 because it's diatomic. And now the problem is it's in grams per mole. I need it in kilograms because of these joules, because of this form of R that I'm using. So if I convert this to kilograms, then I can just kind of move the decimal around. And if I just push the decimal around a little, I end up with this, kilograms per mole. Or you could write it, 2.802 times 10 to the negative second kilograms per mole, however you want to think of it. And now I just plug these values in. So I take the square root of 3 times the R, kilograms, meter squared per second squared, mole, Kelvin, quite the unit, times the temperature, 728 Kelvin, divided by the molar mass in kilograms, times 10 to the negative 2 kilograms per mole. Let's do this. And when I plug and chug through this, kind of see how this thing divides out. My Kelvin will divide out, my moles divide out, my kilograms divide out. And then I take the square root of meters squared per second squared, which gives me a velocity. It just leaves me with meters per second. So when you plug this in, you get 805 meters per second, which is a speed or a velocity, how quickly these things are moving. That's fast, right? 805 meters per second for one of these teeny tiny little molecules. It's pretty impressive. So it kind of gives you a sense of scale for these things at really warm temperatures. You can kind of play around with temperature and see how that impacts the speed. You can play around with the different molecules and see how the mass impacts the speed. And that's kind of how we use these types of things. Now, the reason that I mention RMS molecular speed in terms of gases is to get into effusion. So I want to define a couple terms first. There's diffusion, which you've probably heard of before, because diffusion can be used for a number of different phases. But for gases, it's defined as one gas spreading out evenly through another gas. So if I had a compartment like this, and I have one gas on one side and one gas on the other side, and I take away that partition, then my gases are going to spread out, and they're going to spread out evenly throughout the system, and they're going to spread out kind of through each other. They are going to diffuse through each other. So there's no barrier or anything to those guys mixing together, and that's what they're going to do, is they're going to spread out. That's the behavior of gases. It's the behavior of matter to naturally spread out. Now, effusion is when gas flows out through a tiny pore or a tiny hole in a container. So let's say that I have a balloon that is full of gas here. And if I look at my let's just blow up this little segment of my balloon. Let's say that I have, here's the balloon surface, and let's make it a helium balloon because that's nice and festive. Looks like it's laughing at you. So we have the helium balloon here, and the helium, and you've probably noticed this if you've ever had a balloon over time, even if you don't undo the knot or even if you don't poke a hole in it, the balloon still gets smaller, the gas still leaves. The material that they're made of has enough space in between the particles that these teeny tiny gas particles are going to effuse through those tiny little holes in the container. So it's not like there's like a portal or something that's allowing these things, not like a transport protein through a cell membrane or something like that. We're talking about these teeny tiny little pores that these things can naturally seep through because they're so small and they're moving so quickly. So this is effusion, so teeny tiny, and we have a higher concentration of helium, on the inside, lower on the outside, so it's going to move that direction naturally. Now, Graham's law of effusion says if we do this at a constant temperature and pressure, so if I'm at atmospheric pressure and I keep the temperature of my system relatively constant, then that rate of effusion, so how quickly this process happens, is inversely proportional to the square root of the molar mass. So square root of molar mass sounds like that RMS molecular speed we just talked about. Inversely proportional, so as one goes up, the other goes down. So the rate is going to increase as the mass decreases. Which kind of makes sense, right? If I have smaller mass, smaller particles, smaller amounts of stuff, right? Mass is a measure of how much matter there is, then that's going to increase how quickly these things are going to leave the container. And we can actually measure how quickly this happens, or compare rates of how quickly this happens using Graham's law, this inverse proportionality here. So let's look at an example of this. We're going to calculate the ratio of effusion rates of molecules of hydrogen, so H2, which is elemental hydrogen, to helium, from the same container at a constant temperature and pressure. So a couple things. The rate of hydrogen's effusion is equal to, or proportional to, 1 over the molecular or molar mass of hydrogen. Right, so it's inversely proportional to the square root of the mass. That's Graham's law. So there's this kind of general proportionality here, probably more correct to have the proportional symbol. And the rate of helium's effusion is proportional to 1 over the molar mass of helium. So if we want to calculate the ratio of effusion rates, then I would say, well, let's look at the rate of H2 compared to the rate of helium. And since these guys are proportional and we're talking about ratios here, then the proportionalities are also going to be equivalent. So I can say, well, then 1 over the square root of the molar mass of hydrogen divided by 1 over the square root of the molar mass of helium will give me this ratio, right? So that'll give me by how much more hydrogen, I'm assuming, is going to move faster, is going to effuse through that surface than helium, because we're in the same container. How much more hydrogen am I going to lose? By how much, what speed, by what rate? Okay, so if I do some math magic, then I can kind of combine these guys together. And I'm going to, because I'm taking the inverse of the inverse, flip these around and do this. And then I'm going to do this and actually plug these guys in. So I go to the periodic table and I find that the molar mass of helium is 4.003 grams per mole. And my hydrogen is 2 times my 1.08. Okay, so when I plug that in to my handy-dandy calculator, I get 1.409. And what does that mean? Well, what that means then is that hydrogen effuses 1.409 times faster than my helium. I set up my ratio to see kind of by how much larger is this guy than this guy. You could have flipped it the other direction, and this would have been a less than 1 number, and that would have been fine too. You would have said that's how much faster helium is, knowing that it's slower. So it doesn't matter which way you set this kind of problem up. But the interpretation of this result then is that H2 effuses the 1.4 times faster than helium because of its smaller mass. Okay, so that's one way to use Graham's law of effusion. It wraps up and uses that RMS molecular speed and kind of gives us a sense of how quickly these things are moving around. As always, if you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.